Today, I'm going to be talking about the Division of AI Research at QMIND. We're going to start off with a little bit of history. How did DARE come to be? How did it kind of establish itself in a growing QMIND? So flashback to 2017, where Cooper Majoni and team started QMIND. They won Club of the Year that year, which allowed them the next year to expand to over 100 people. There's me, a couple pixels in the back there, and my team from my first year on QMIND. This year, we really garnered a lot of industry connections, and it was the first year that Q got the funding and allowed us to really explode the next year into over 200 members. Again, there's me in the back, a couple pixels. And one thing that this fantastic amount of growth allowed us to do was to get some more funding for certain initiatives. Jeremy Kulchik, who was a master's student, who is now working on the Canada arm, doing some, or will be shortly. But what he wanted to do was he saw a gap between the opportunities that undergraduates enjoyed and that graduate students enjoyed in robotics and computer vision. So using some of that new funding, QMIND purchased 3 Turtlebot waffle pie robots, and Jeremy started DARE. And the goal of DARE is to connect undergraduate students with graduate level opportunities in computer vision and robotics. And so a couple of the past things that we've worked on. So if you want to see more of what we've done, look in the proceedings of QChi, and you can find projects from all design teams in QMIND and DARE. So one of the projects that they highlight was using reinforcement learning in Gazebo. So basically they simulated different maps and they tried to get a robot to navigate and plan its path using reinforcement learning. They used a form of reinforcement learning called deep Q learning, where they use a kind of a deep neural network to find a policy that allows them to navigate a state to maximize a reward function. And so this was some really cool work. I'd also like to highlight the work by Sam Cantor's team, Robotic Object Detection and Autonomy. They did a lot of work trying to get kind of one of the newest state-of-the-art object detection models, YOLO v3, to run on the Turtlebot hardware. So they built a library that allowed it to run on the robot, and here it is. And they did kind of like a search and rescue type task with it. It was a lot of work because YOLO v3 is built on Python 3 and ROS Kinetic was on Python 2. So that was a huge challenge they overcame in our first year being DARE. And of course, there was my team, Robotic Traversal and Pothole Avoidance. Basically, we spent the first half of the year trying to look at how sensor data could indicate the level of surface you were driving over. And then we spent the second half of the year looking at how we can get a robot to automatically detect, localize, and avoid a pothole. And so this year, we've leveled up a little bit. DARE has expanded once again, and we have added 3 Intel RealSense cameras to our hardware library. And what these cameras are is they're RGBD cameras. Capture a normal RGB image, but they also capture the depth at every point. And this allows you to create cool depth maps like you see here. This gentleman is striking a pose, and the Intel RealSense captures that with a color mapped depth map. And this allows us to really expand our computer vision capabilities at QMIND and at DARE. That's kind of some of the projects that we have going on this year. And I don't want to give too much details because all of that will come out in the demos at QChi. So definitely come to that. But yeah. And now I'm going to talk a little bit about my work from last year. So this was my team from last year, and we were the DARE Robotic Traversal team. And what we did was the first half of the year, we had the initial goal of taking in camera data and trying to predict how difficult to traverse the terrain ahead was. And so what we had to do that with was the Turtlebot 3 waffle pie robot, which is quite a name, but it's actually a really cool piece of hardware. And using the robot operating system, it was quite a powerful tool to kind of explore robotics for the first time. So what we had access to was the Raspberry Pi camera on the robot, the inertial measurement unit, and odometry. And those were kind of the things we needed to do this project. And so initially, we thought instead of trying to go right from camera mapping onto IMU data, which is a very challenging thing, we tried to do one link in that chain to start. So we tried to go from IMU data to which surface the robot was driving on, with the thought that if that proves to be not plausible, then it means the whole endeavor is probably not plausible with the hardware we have. That way we didn't spend a whole lot of time developing models for the vision and then realize that we couldn't actually map it to the sensor data. And so what we did is we designed an experimental procedure and we collected data of the robot driving on different terrains that we would qualitatively say have different difficulties for the robot. And so once we collected the data, it was a matter of data visualization, data analysis, data clustering, that kind of stuff. So we use principal component analysis to visualize our data. You can see that there's some interesting patterns in this. Obviously in presentation mode, I can't spin this around and let you actually look at it in 3D, but you can see surfaces that are more similar to each other actually have a similar distribution. And different surfaces do have slightly different distributions. So for example, ceramic tile and laminate tile should be very similar. And in fact, you see that with their points being clustered here, the red and the purple. Now, the issue that you might notice if you're trying to do any sort of prediction task is that these clusters are definitely not well separated, right? They have different distributions, but if I gave you a point that was like here, you couldn't really tell me which surface that was from. And so that proved to be an issue when we tried to do the classification. So first we tried some classical classification models, such as logistic regression, k-nearest neighbors, and k-means. Logistic regression actually performed the best out of all of our models, but it was still not great, right? And that goes back to the PCA plot. If I give you a point right here, it's really hard to tell what class that belongs to because the data is not separable with the data we have. We also tried k-nearest neighbors, and we looked at the k-means clustering to see if that overlapped well with the actual classes of the data. Next, we tried some deep learning. We figured maybe there were some nonlinear relationships, although it seemed unlikely, but it was worth exploring because you would imagine that different surfaces would, like the forces would vary linearly. Like the forces wouldn't interact in any nonlinear kind of way because that's like not really the physics at hand. But we gave it a shot with an LSTM, which is long short-term memory network, which is kind of like a recurrent neural network. We got, again, 53% testing accuracy, so not great. Again, data is not very separable. So we realized that, okay, we kind of need to pivot because we can't really expect to be able to map from camera image to IMU data if we can't even map from IMU data just to the surface, let alone a picture of the surface, right? So next we, so we swapped to looking at the discrete event of driving over a pothole and specifically how to avoid that event, because that's obviously very useful for a robot, especially one as kind of with low ground clearance as the Turtlebot. So we collected videos of potholes. This was a real big pain. So obviously there's a couple components we need to make for this project, right? To avoid a pothole, you need a couple things. You need to be able to detect if there's a pothole. You need to be able to see where in the image the pothole is. You need to be able to translate that to real world coordinates. So instead of knowing that it's at this pixel, you need to know it's like this many meters ahead and to the left. And then you need some sort of algorithm to avoid it. And so the issue was that there's not a great data set of potholes for object detection, for localizing them. We could get potholes from Google Street View, and there was a data set of those compiled. However, that data set is taken from the height of a car, right? And actually slightly above a car, because that's where most of the sensors are in the Google Maps trucks. But our robot is about 6 inches off the ground, so the potholes look vastly different. So we can't really expect a network to be able to generalize from seeing a pothole in a couple small areas of the image versus, a pothole like the one on the screen filling a very good percentage of the ground. So basically, every time we walked to class, back in the times when we had to walk to class, if we saw a good pothole in the street, we would stop, crouch down low with our phones and take a video of it. And then we would split that video into frames and use label image to draw a bounding box on each of the potholes. And this was a very time-consuming process, but we annotated a data set of about 5,000 images. So obviously, if you've done machine learning projects, you know that most of the time is spent getting the data, getting good data, and cleaning the data. We also use data augmentation, which was really huge. So data augmentation is the idea that you add random noise and you add variation to your data set. So we took every image and we would, when we actually fed it, and I'll show this in my code walkthrough, but when we actually fed it into the network, it would be randomly flipped, rotated, the brightness would be changed, and it would be moved a little bit. And this allowed the network to essentially see more potholes than we had images of, right? Because if you flip potholes, then essentially you have double the amount of images. If you rotate them, you have more. If you change the intensity, translation, etc. So we trained a convolutional neural network to classify whether it was a pothole in an image. It went fairly well. Again, we had a data set of about 5,000 images to train on and 1,500 to test on. And our model takes in a 128 by 128 RGB image, and it'll put 0 or 1, is there a pothole in there or not? Next, we train the localizer. So again, takes in the same kind of image, and instead of outputting a yes or no answer, it does regression on 4 variables. So it outputs a value for X, for Y, width, and height. So those 4 variables can define the location of a pothole and how big it is. And that's what produces the bounding boxes there. So for this one, you can see our data set was a little bit smaller. That's because we only trained on the images that did have potholes, because we were just looking at where in the image is the pothole. Now, how do we tie this all together? So the robot operating system works by a set of nodes that can all communicate together by sending messages over channels. And so we made a node that runs and it constantly tries to detect if there's a pothole in image using our model. We have a localizer node that runs the localizer and says, okay, if there is a pothole, where is it? Then our logic module will calculate the angle that it needs to drive at to avoid the pothole. And then we drive past it and return to course. So our models actually performed fairly well. You can see that the training graph looks nice and smooth. And actually an interesting point is that the validation loss is less than the training loss. This might seem counterintuitive, but it's often the case with when you're using data augmentation. Because you use data augmentation on the training data to increase the amount of variation you see, but you don't use it on the testing data because you don't want the test to be any harder than it needs to be, right? You want it to be as if you were seeing new data in the real world for the first time. So it's actually usually easier to do it on the testing data sometimes because it doesn't have these like rotations and skews and brightness changes and stuff. The only issue that I will mention is that we didn't get a large number of different potholes in our data set just because it was a lot of effort to find a new pothole that worked and that kind of stuff, right? So physical time constraints. So I believe that our model is overfit to a couple potholes a little bit, but it still performed fairly well at the task. And so another challenge was how do we actually demo this at the conference, right? What we ended up doing is, remember how I said that the robot operating system is a set of interconnected nodes that communicate by sending messages to each other? Well, the camera is a separate node and it sends the image messages. The nodes we made that control the robot send messages. And so what we did is we captured all of those messages as we let our robot avoid a pothole in real life. And then we replayed that at the conference. So instead of having to dig a hole and make a pothole in the middle of the conference center, we're able to just place the robot down on the floor and play back the actual sensor data. And that way we could show people on a monitor what the robot was seeing and have the robot actually think that it's seeing outdoors and see the pothole, and then it avoids it. And we had binders set down to mark where the pothole was. So that ends the presentation part of the presentation. Now we're going to hop over to the code walkthrough. Stop sharing my screen briefly as I navigate to GitHub. All right. I'll increase the zoom because I feel like the text is probably pretty small. So the first thing I want to look at, and again, this code is all public, so you can just go to RoboTraverse on GitHub. And there's basically semester 1 work is in sensor data analysis, where we do clustering and classification on the inertial measurement unit data. And pothole avoidance is our semester 2 work, where we develop on the robot operating system to avoid potholes. So I'll quickly go through sensor data analysis, specifically, let's go to logistic regression. So to start, we import our libraries. So we're using sklearn to do the logistic regression, as well as feature selection. We're using Plotly to visualize our work. And yeah, so we have these CSVs, which are the different inertial measurement unit data that we've exported from ROS-bag files. And so one of the interesting things, so this task involved trying to decide which surface you were driving on from the inertial measurement unit data. But the data is in time series. So each time series only has data pertaining to that exact instant, right? What's the acceleration? What's the velocity? And so I don't think that it would be possible to identify what surface you're driving on from the data at one instant. I think you need to see the data and how it changes over a couple instances to be able to hope to make a guess at what surface you're driving on. So for that reason, we actually, after some basic pre-processing, we took each row and we computed the difference between this row and the previous time step and several other time steps preceding it to get what I'm going to call delta columns. So just if it's acceleration in the x direction, then acceleration in the x direction, delta 21 would be the difference between that row and 21 rows ago. So that allows a model that takes in one example to have like a historical understanding of the forces. And so basically that's just some, with practice with pandas, stuff like that becomes a little bit easier, and that's kind of what this is. So you'll notice we adjust the index, and then we interpolate not a number values using a polynomial, linear fit actually. And we drop incomplete entries. And then here is where we actually create the delta columns using the .diff method of pandas series. Yeah, so then we did feature engineering. So because we had all these delta columns, we had a lot of features, right? Our data frame was now 145,000 rows by 530 columns. And so what we wanted to do was get only the best features, and that way our model would run a lot quicker. So also, there was kind of a big challenge in this work was that some of the features kind of served as markers. So with any learning algorithm, you give it an input and it's going to try to find the easiest way to optimize a cost function, right? So it's going to try to find the easiest way to identify the surface. And actually, it knew the orientation of the robot when we started each run. So each trial where we collected data on the surface. And that orientation, we drove it straight and we didn't turn it around because we figured that would introduce different forces. We wanted to just feel the bumps of the surface. And so it actually, at first, when we ran the K-best feature selection, that kind of told us that the best features were actually just like the orientation of the robot. And so our model was actually looking at which way our robot was facing, and based on that, it could tell which trial number it was, and it knew that trial number this was likely this surface. And so that was a common theme with all of our models, is that we had to eliminate the features that turned out to be kind of markers. So unfair features that you wouldn't have when you are actually testing your model. So once we did that, so we removed certain marker features and then we took the K-best features. Then we just fit our model on the data set, and we had a reasonable accuracy, nothing to write home about. If the accuracy had been better and the data was more separable, we would have kind of dived a little bit more into which features contributed most and kind of look at F1 score, look at the balance of precision and recall. But from these results, it was clear that the data was not linearly separable. And so then we looked at some deep learning and found that that didn't work much better either. So let's hop over to the pothole avoidance. So let's start at the notebooks. So for pothole localization, again, we're using keras on top of TensorFlow. So we load in our data from different bag files. And for every bag, basically, so we're training a localizer, so we need to load in the images, but also the annotations. The annotations were saved in XML format. And so we read those in, and then we converted that to a data frame that had, so width of the image, height of the image, and then where the pothole was in the image, as well as the file name and the image file path. And so once we had a data frame that was the annotations for the images, we actually loaded in the images using a function retrieve image. So it uses the Python image library and converts to RGB, resizes it and normalizes it, divided by 255, and converts it to a NumPy array. And so using that, we apply that on our label data frame. And so we have an array of images and an array of labels. And then we divide into training test splits. And then if you check the shapes of our data, you can see that we have just over 3,000 training examples, 850 testing examples. The shape of the input is 128 by 128 by 3, and the output is 4. And that obviously is X, Y, W, H. One actually really interesting challenge we had. So for classification, a common form of data augmentation is to rotate the image, and we wanted to do that for localization. But images are easy to rotate. The difficult part was rotating the bounding box, because we couldn't just take the box and rotate it, because that's not how bounding boxes work, right? You have to have, it can't be any parallelogram. It has to stay a rectangle, and it has to be aligned with the coordinates of the image, right? So the way we found to actually rotate it was to convert to polar coordinates, because although it's difficult to rotate a set of coordinates in Cartesian space, it's much easier in a polar coordinate space. And so that was kind of the idea behind rotating the coordinates. That was a nice spot where kind of something I had learned in vector calculus like a month before came in super clutch in work I was actually trying to do. So that was really cool. And yeah, so remember how I said that the data augmentation would happen when the model pulled more images? So this is the class that actually does that. So Keras on TensorFlow allows you to define a pothole batch generator. And kind of like a Java interface, you have to implement a couple methods. So you have to get the number of batches. You have to have a function that runs on the end of one epoch, and you have to have a get item function. And the get item is supposed to return a batch of images and labels. And so what we do is we randomly flip the image if it is trained, because obviously we don't do this on test. On test, we just return the images. Yeah, so we randomly flip. We randomly multiply the brightness by some factor. We randomly rotate a certain angle, right there. And we randomly shift the image. And so then we just return X and return Y, where X and Y are a batch of images and labels. And so we create the generator. Oh, this is just looking at the images. So this is one example batch of images that we generate. You can see that these images are rotated, but the bounding boxes are still locked onto the pothole. This would not be the case if we didn't actually transform the coordinates like we did. And then we design our model. So this is kind of the part everyone gets excited about, but it's really kind of one of the easier parts. So it's a pretty simple convolutional neural network. We take in the input shape defined by our size variables, ReLU activation on all the convolutional layers. We start with 16 filters, and then we double that at each block. And that way we start to look at bigger and bigger features. So at first you're looking at small edge, and then maybe contour, and then pothole. Yeah, and so we use dropout, so our model to combat overfitting a little bit. And you'll see in a lot of convolutional neural networks, there will be convolutional layers, either one or two. We end up going with one in each block, followed by max pooling and dropout. That's a pretty standard kind of design. And so we have our convolutional blocks, and then towards the end, we have a dense layer to kind of take all of the features and non-linearly make a decision. And then we have our final dense layer, which takes the last features from the 128 node layer down to just 4 nodes. And you'll notice that we have linear activation on that last node. And what that means is that each node will have a value between 0 and 1 that indicates the kind of the portion of the image that that value is at. So if X is 0.5, then it means the pothole starts at X equals half the image. And so each of our 4 output nodes will represent X, Y, W, and H. Again, the model summary, personally, I find it more intuitive to look at the actual code to kind of understand the model, but this is useful too. We compile our model with the atom optimizer and the mean squared error loss function. And finally, we train our model using a test generator and a train generator. And then we fit our model. So you can see it training, and then it generates this nice loss curve. So finally, we're going to visualize some results, and this is what the localizer looks like. So you can see, I believe the green box is what the pothole is, and the red box is what our model thought it was. So you can see that in most cases, it's pretty good. Some cases it's a little bit off, but yeah, and you can use like, if you're using this on a robot, you can use like a smoothing function. So if it's on each frame, if it's estimating the potholes, like the estimate's jumping around a little bit, you can kind of smooth that. But yeah, so that's the basics of how we made a model that took in an image and outputted a bounding box on where the pothole is. Yeah, and so basically, then we made ROS modules. So for example, the localizer node basically calibrates the camera. It makes so this is like robot operating system stuff now. So we make a publisher that's going to publish an image, and we make a subscriber that's going to subscribe to the actual camera image. And so this node is taking the data from the camera and outputting its own image with a bounding box added. And we're also subscribing to Chatter, which is a text channel that we're using to communicate between our nodes. So we get the TensorFlow model loaded up. So if pothole is present, and that is determined by the classifier node, then we start working, and our callback function is where the magic happens. So we get the image, and then we make predictions, and we create a rectangle, convert the bounding box to real world coordinates, and then we publish that. And so our logic node has the data required to avoid the pothole. Yeah, I'm not going to go through all the code in all of the modules, because that's probably a little bit beyond the scope of the presentation, but it's all here if you're curious, and it's fairly well commented. So with that, thank you for listening. That concludes the code walkthrough part of the presentation.